So this is question number 45 of the Fields and the Capacitors homework booklet. So in question 45, what we start off with is we start off with a figure that shows a capacitor, and this capacitor has a capacitance of 370 picofarads. And this is our diagram here. This capacitor is made up of two parallel metal plates, and the area of these metal plates is 250 centimeters squared. And between these plates is a sheet of polythene that has a relative permittivity of 2.3, and it completely fills all of the gap between these plates. And what we want to do is we want to calculate the thickness of the polythene sheet. So if you think about it, the thickness of this polythene sheet is going to be equal to the distance between these two plates. Now we have an equation that tells us what the distance between these two plates are in terms of the capacitance, and that's this one here. So we can calculate the capacitance of a capacitor if we know A, which is the area of these plates, which is here, which we do. If we know this quantity, which is the permittivity of free space, and we can get that number straight from our data booklet. This is the relative permittivity, which is 2.3, so that's this one up here, and D is the distance between the plates, which is what we need. So provided we know the capacitance, which we do, we can rearrange this equation to this, and then simply put our numbers in and work out what the thickness of this polythene is, in other words, the distance between these plates. The only very slight trick here is that we need the area in meters, and in square meters, and we've got it in square centimeters, so we have to convert square centimeters into square meters. The way that we do that is we take our square centimeters and we divide it by 100 squared, so 100 times 100, because there are 100 centimeters in the length part, for example, and 100 centimeters in the width part. And if we do that, our area will therefore be 2.5 times 10 to the minus 2 square meters. We can take all of the numbers we know and simply substitute them into this equation now. So 2.5 times 10 to the minus 2 is the area. This is the permittivity of free space. This is our relative permittivity, and the 370 times 10 to the minus 12 is the capacitance of our capacitor. And if we do that, then we get 1.38 times 10 to the minus 3. Simply writing this to the same number of significant figures that were given in the question gives us 1.4 times 10 to the minus 3 meters. In terms of marking points, you get your first mark basically for putting these numbers into this equation correctly, and you get your second mark for getting the correct answer. In part B, we're given lots of information to start off with. So we're told that the capacitor is charged up so that there is a potential difference of 35 volts between the plates, and that the charge on the capacitor when the potential difference is 35 volts is 30 nanocoulombs, and when we have a potential difference of 35 volts, the energy stored is 0.23 microjoules. So we charge this capacitor up and then we disconnect it, so it's not connected to anything whatsoever, so it stays charged up. And then we pull the polythene sheet out from between the plates. The capacitor isn't discharged and the separation between the plates stays exactly the same. So we end up exactly with this diagram up here, but instead of polythene in between it, we simply have air now. So to start off with, we need to show that the potential difference between the plates is about 80 volts. So what we're going to do is we're going to consider this equation over here. And this is the equation that we kind of used in the first place. And if you think about it, so this is the capacitance that we started off here. Now if we change the relative permittivity here, then for the distance to stay the same, the capacitance has to change in order for this thing to stay the same. So if we change the relative permittivity, it changes the capacitance. So in order to work out the potential difference, the very first thing we need to do is, because capacitance depends upon potential difference, we need to calculate the capacitance. So with the polythene, we're told it's 370 picofarads. Without the polythene, if we think about it, the capacitance is going to be smaller, because when we put air between it, this ER bit, we should know this is something we need to learn, the relative permittivity of air is 1. So basically, if you think about this equation here, if this goes down by 2.3, then the capacitance has to go down by a factor of 2.3 in order for the distance to stay the same. So that's what this equation says here. Basically, our new capacitance is equal to our old capacitance divided by our relative permittivity. In other words, divided by the 2.3. So if we do that, we get 370 picofarads divided by 2.3 gives us 161 picofarads. That's worth 1 mark. But we've not yet answered the question. We now want to know what happens to the potential difference. Well, if we go back to our bog standard equation that links capacitance and potential difference, the potential difference is the charge divided by the capacitance. The charge isn't changing. The charge can't change because the only way you can change the charge of a capacitor is to charge it up or discharge it, and we know that's not happening, so that stays the same. So if the capacitance changes, the potential difference changes. So if we just take the charge that we've got, the 13 nanocoulombs in our question up here, and we divide it by our new capacitance, the capacitance that we worked out over here, then it will give us our new potential difference. And if we do that, then we end up with 80.74 volts. And again, you need to show that you get this particular number over here. If you do that, then that's worth your second mark. So you've shown that the potential difference basically increases to 80 volts. So now what we need to do is we need to calculate the energy that's now stored in the capacitor. So this is fairly straightforward. This is an equation we use all the time. So the energy is simply a half CV squared. C is the capacitance of the capacitor. Well, that we've worked out up here. So that's our new capacitance. V is the new potential difference, which is the 80.74 volts that we've got. And if we simply substitute both of those into the equation, we get 0.52 microjoules. Again, in terms of marking points, putting the correct numbers in is worth 1 mark. Getting the correct answer is worth your second mark. We then have to explain why it is that there's an increase in the energy when the polythene sheet is pulled out from between the plates. And this is kind of a little bit tricky. So we have to understand what actually happens to with a dielectric inside the capacitor. So when the sheet's inside the capacitor, the polar molecules that are inside the dielectric, so polar molecules are one where there's a positive part at one end and a negative part at the other, they align. So the positive end of the polar molecule is attracted to the negative plate, and the negative part of the polar molecule is attached to the positive plate. So basically your dielectric becomes charged up. Now when you pull this sheet out, what you have to do is you have to do some work in order to do that, because the positive part of the dielectric that's formed by all of the positive charges aligning up is attracted to the negative plate. So you have to do some work to separate them out. So when you separate them out, you do some work, and that work is transferred to the capacitor. So your 2 marks are 1 for saying what happens with the dielectric and saying that the polar molecules align so that the positive charged end is attracted to the negative plate, and that the energy of the capacitor increases because you have to do work on the capacitor to separate the positive surface of the dielectric from the negative plate, and this work is then stored in the capacitor, and that's worth 2 marks. So that's your first marking point, and then this second sentence is your second marking point. So that was question number 45 of the electric fields and the capacitors homework booklet.